Hello, everyone. This is the first introductory video in the series Assembling the PHP Puzzle. It will consist of two parts, theory and practice. The goal is to assemble a mental map of the semantic entities that make up the world of PHP, and then explore each of them separately, while clearly understanding their place in the big picture. In general, we need to build a foundation, but not about boxes with variables, but one that clearly describes how the technology works and what elements it consists of. At first glance, this material may not seem very useful from a practical point of view, but that is not the case. A fundamental understanding of the principles of technology paves the way from magical thinking to engineering clarity. It is a transition from trial and error to conscious creativity, that is, from amateur to engineer. Speaking for myself, about 10 years ago I first asked myself the question, what is PHP? I wanted to understand the big picture, but with a fairly high level of detail. The official documentation, although one of the best, did not fully satisfy my request. So I started putting this puzzle together on my own, while using PHP in my work. This is the puzzle we will be assembling together in this series. Let's start by looking at a simplified diagram of how compiled and interpreted languages work. Here we see that we have source code in a programming language, for example, C or Go, and we have a compiler. We can pass the source code to the compiler. The compiler will perform some transformations and obtain a binary file. This file will be returned by the compiler as the result of its work. As a result, we will have a binary file on our disk, which is a program, that is, a file that can be run on the operating system. If we run this file, we will get the process of executing the instructions of this program in the context of its data. In other words, the scheme can be described as follows: code, compiler, program, process. The main thing to note here is that after compilation, the source code in C or Go becomes a standalone program that can be run. Now let's look at the working scheme used in the world of interpreted languages using PHP as an example. Compared to compiled languages, it may seem that PHP is not really a programming language, since there is no program, that is, no executable binary file, that is compiled from PHP code. For PHP programmers, there is not even such a thing as a PHP code compiler. In other words, a completely different sequence of actions is used here. Let's take a look at it. The first thing that starts in this scheme is the interpreter. For clarity, let's define the terms. An interpreter is a ready-to-run program written in the C language. This program can interpret and execute algorithms written in PHP. After the interpreter is launched, a process appears in which the interpreter's instructions are executed in the context of its data. The interpreter will receive the path to the file describing the algorithm in PHP, execute our algorithm, and return the string result to the output stream. It is important to note that the operating system launches the interpreter process. In other words, the program written in C and compiled into an executable binary is actually running. It takes the path to the source code in PHP, reads it, and then converts it into something like a binary file inside itself. That is, it parses the source code, converts it into an abstract syntax tree, compiles it all into opcodes, and then executes them directly inside itself. It's just a different execution scheme. There is no standalone executable file, that is, no program, but there is a final meaningful result, the process. And the applied logic or algorithm executed by this process is described in PHP. In other words, PHP code does not become a program, it becomes instructions for another program. Let's summarize. PHP code itself does not turn into a separate binary program. It always runs inside the interpreter process. An interpreter is a program that contains only internal technical logic that allows interpreting and executing algorithms described in the PHP language. Without it, PHP is useless. What we have already learned is, in principle, a good foundation for successfully solving many practical tasks in PHP, but let's go further and learn more. The first thing we want to start our dive with is the division of the concept of PHP into two branches. The first branch of PHP as a language is a set of rules for writing source code suitable for the PHP interpreter. They are described in an informal specification on the PHP.net website. If a script complies with these rules, it can be passed to the interpreter so that it can execute it. We will deal with this topic separately, so I will not go into it any more than is necessary at this point. The second branch is PHP as an interpreter. I will focus on this topic, as I believe it is where most misconceptions are delusion. The PHP interpreter can be divided into three main components. These are the SAPI interface, the Zend Engine, and the engine's extension system. Let's take a closer look at each component, paying particular attention to the concept of SAPI. The slide presents SAPI as a kind of mechanism or software layer between the core and the process data. But I want to look at this topic from two perspectives. First, from the perspective of a PHP programmer. SAPI is an environment profile, that is, a specific set of populated superglobal arrays and methods for working with input-output. For example, when you work with PHP code on the web using, say, php-fpm, you have the usual set of superglobal arrays server, env, and so on. But if you run the code in a terminal using the PHP console interpreter, you will find that only 3 superglobal arrays are populated, while the rest are empty. This is SAPI, or more precisely, the result of its work. For a PHP programmer, SAPI is an environment profile that defines both a combination of filled and empty superglobal arrays and the available mechanisms for working with input and output. For example, the constants stdin, stdirr, and pseudo-streams stdin, stdout, etc., which are specific to a particular environment and launch. SAPI creates an environment profile in the corresponding environment. And since there are several launch environments, there are also several possible SAPIs. Let's look at this in a little more detail. If you use a PHP interpreter for a terminal that runs as PHP, the file name and which was compiled SAPI, only 3 superglobal arrays will be filled. That is, we can say that a CLI profile will be created. The server, globals arrays will always be filled, and env, as we see on the slide, only when certain conditions are met. Input-output is handled through the constants stdin, stdout, stdirr, or the pseudo-streams stdin, stdout, and stdirr. If you use a PHP interpreter for the web, such as php-cgi or compiled CGI SAPI, then SAPI will fill all arrays, that is, create a conditional web profile. Of course, this is provided that data is transferred to these arrays. Then we can use any of the superglobal arrays in our code. Working with input-output is done through the PHP pseudo-streams input, output, and stdirr. The constants stdin, stdout, and stdir are usually not declared. But if you use a modern PHP interpreter for the web, php-fpm, which is compiled with FPN SAPI, then it will be a special case. It's not just an environment profile, it's a whole system. I will discuss it as a separate topic, so I will be brief for now. It consists of a daemon that listens for connections via a socket or over the network. Inside it, there is a master process and a pool of running interpreters workers. SAPI distributes requests between these workers and exchanges data with the web server that made the request using the FastCGI protocol. But for a PHP programmer using php-fpm, this is a normal full-fledged web profile, similar to using CGI. From an environment perspective, input and output are handled through separate special pseudo-threads, PHP input, output, and stdir. The constants stdin, stdout, and stdir are not usually declared. Now let's look at how SAPI works from a technical perspective. SAPI is an interface in a running interpreter between the Zend Engine core and data coming into the process from the environment that called the interpreter. This definition is accurate when referring to running in a terminal or in the now obsolete php-cgi. That is, when a PHP or php-cgi process is simply launched, instructions are executed, and the process is terminated. When using php-fpm, as I mentioned earlier, SAPI has evolved into a full-fledged system with a set of components. In practice, PHP in FPM and PHP in the terminal are usually used. In some advanced cases, certain versions of synchronous PHP. I will discuss them, but not now. I mention CGI only to understand the general logic of how it works. Historically, CGI was the first option for running PHP, and it was built on principles that were and are still used today for standard program execution in the terminal. That is, initially there was a certain principle for running programs in the terminal. Based on this principle, a method was developed for running PHP code through the php-cgi web server. And then, based on the same principle, an interface was created for running PHP code in the terminal. Let's examine these principles and understand the general logic, as it forms the basis for comprehension. Suppose we have a bash script and a process in which a terminal with a bash shell is running. In this process, we call something like bash script _name.bash. The shell understands that we want to run the script. Next, it performs some preparatory actions, and then the fork system call is executed. That is, it addresses the operating system and says, "Create a copy of me." The operating system copies the data structure of the shell process into its memory. All data from the parent process is transferred to this child process in copy-on-write mode, including I/O streams. The operating system then resumes execution in these two processes. In other words, the result of executing fork in the parent process is to return control to the processes simultaneously. Now they both continue to run in parallel, starting from the point where the fork function returned. In pseudocode, it looks like this. Somewhere in the parent process, a check is performed to see if the current call is an execution call. If so, the parent process collects the set of parameters that were passed during the call. This is bash and script name bash. This is bash and script name bash. As an argument, the parent process searches for the location of the actual binary, assigns this data to a variable, collects the entire set of environment variables, and calls the conditional function startExec. Inside this function, a fork call occurs, resulting in a split. And then both processes start from this point, that is, from the point of return of the fork function to the variable period. And the fork function can return three different values. If it is a child process, it returns 0. If it is a parent process, it returns the ID of the child process. It can also return -1 if an error occurs. In general, the exec system call is invoked within the child process. It passes a set of arguments. This tells the operating system to take the bin bash binary and replace it with the instructions and data of the child process's memory, as well as set the call parameters and environment variables. It is important to understand that, ultimately, the child process has a copy of the parent's file descriptors, variable environment, and parameters passed during the call, as well as a running instance of the bash interpreter and a script with an algorithm in bash. This is a standard set of data for passing to the interpreter. This scheme was taken as the basis for the development of php-cgi. It was intended to be run by a web server, that is, in the context of the HTTP protocol. In a nutshell, HTTP is a protocol that defines the rules of communication between a client and a web server. It has a number of methods, such as get, post, put, patch, and so on, which determine the semantic intent of the request and the generally accepted type of request defined by the method. Here, for example, is a typical GET request. Here we see the start line. Request line, which specifies the HTTP GET method, the path to the requested resource search, the query string parameters, and the HTTP1 protocol version. This is the first line of the request. Below are the HTTP headers, which convey additional information about the request, and a typical request using the post method. Here we also see the first start line of the request, followed by the request headers. And unlike the GET method, it is assumed that there may be a request body. For an HTTP request addressed to a PHP file, the server parses the start string and HTTP headers and lays them out in environment variables, and places the request body, if there is one, in stdin. Everything else is identical to the process of calling in the terminal. The web server makes a fork call. Then, inside the child process, exec is executed with a set of arguments. The OS replaces the memory of the child process with the instructions and data of the bin php-cgi binary and passes it the environment variables and parameters. When using CGI, the web server only passes the name of the file requested for execution in the parameters. That is, the same data is sent to the running php-cgi process as when, for example, a bash script is run in the terminal, that is, according to the general principle. Later, CLI SAPI was also created, which allowed PHP code to be run in the terminal based on the same logic. Next, when the php-fpm process manager was created, it was decided that FPM SAPI would provide the same set of arrays as classic CGI, so that PHP programmers could work using their familiar web profile without having to think about the fact that PHP code was being executed in a different way. After such a long explanation of how SAPI works, let's move on to the next component. This is the Zend Engine core. I won't go into as much detail here as I did with SAPI, as the core will be discussed separately, but I will point out the key points. The kernel is responsible for parsing the source code, that is, it parses it and converts it into an abstract syntax tree AST. It then compiles the AST into opcodes and executes these opcodes within its virtual machine. In the narrow sense of the word, Zend Engine is an interpreter, that is, it is the brain and hands of the interpreter. This is sufficient for a general description. Let us move on to the last component. This is a set of extensions. There is a special system for modular extension of the Zend Engine core functionality. Extensions are add-ons that can be compiled together with the SAPI core into a binary or connected separately as dynamic modules via the PHP-ini file to an already compiled interpreter. These modules are add-ons to the Zend Engine core, which uses its API to add new functions, classes, interfaces, types, wrappers over system libraries, and so on. In other words, they extend the capabilities of the core, but are not part of it. We will cover the topic of extensions in sufficient detail, but also in a separate analysis. So, let's summarize the interpreter. The final form of the interpreter is a binary file compiled from C source code. There are several basic types of compiled interpreters. This is PHP for running code in the terminal. php-cgi for running code as a server language, an outdated approach. Mod PHP is a dynamic module for Apache, not a separate binary. It is a special type of interpreter that runs within the Apache process. This is also an outdated approach. There is also php-fpm. This is a daemon that works using the FastCGI protocol. It is the de facto standard today. In general, in other words, an interpreter is the result of compiling the Zend Engine core and its extensions with various SAPI options. There is only one core variant, but there are several interfaces for running it. This concludes the theoretical part, and we will now move on to the practical part, where we will consolidate all the material we have covered. I will launch Debian 13 on VirtualBox and conduct the entire demonstration in the terminal. At the start, behind the scenes, I performed several basic actions. These were port forwarding in the network settings. To make SSH and HTTP requests from the host OS to the guest OS, I added the main user to the sudo group and installed php-cli for the terminal and the microconsole editor. The text description of the video has instructions on how to do this if you also use VirtualBox and Debian. So, in the theory section, we learned that there are different environments for running PHP code. These are web via CGI or FastCGI, as well as running in a terminal. There is another option that uses a module for Apache. This is Apache plus mod PHP, but I will only touch on it briefly, as it is not as important for a fundamental understanding as, for example, CGI, and is rarely used in modern production. Today, the accepted approach is that each tool performs its own specific task. The approach where a web server performs its main task, that is, serves static content, and at the same time launches an interpreter in the same process, is outdated. Nevertheless, it can still be found in many older projects. If we look at the Apache web server, for example, it can run PHP code using both the CGI and FastCGI protocols. For example, Nginx cannot run CGI, but it works perfectly with the FastCGI protocol. We will not delve into how a web server works. It is only important for us to understand that it accepts HTTP requests, parses them, and calls PHP code execution in the context of the data received in the HTTP request. As I said earlier, FastCGI is most commonly used in modern practice. But in order to understand it, you first need to understand how CGI works. Since its concepts form the basis of FastCGI, we will need to start with the Apache web server. So, let's install Apache 2. Enter the password and agree to the installation of dependencies. Now, if we go to localhost 8888, which is the port I specified when forwarding VirtualBox ports, we will see the Apache to welcome page. Here we see that the configuration files are located in etc Apache to directory, and the HTML page itself is located at var www.html. If we go to this directory and create a PHP script in it, Write some valid PHP code in this script. And try to call it with a web server. Apache simply returned the text representation of this PHP code to us. This means that the web server can distribute static files by default, but cannot run scripts written in any programming language. In short, it doesn't know what to do with PHP files. This means we need to teach the web server how to run our application scripts. Since we are talking about a web server, we can either install the PHP module so that the Apache process has a built-in PHP code interpreter, or use the php-cgi interpreter. As I said earlier, we will not install the PHP mod, as this is an outdated approach and is of no use from an educational point of view. This means that our choice is the php-cgi interpreter. To give a brief introduction, the CGI protocol was invented so that a web server could run programs written in different programming languages. In other words, the CGI protocol arose as an answer to the question of how a web server would run programs. And this protocol was built on the classic principle of running programs in a terminal. This means that we need to digress and examine how programs are run in a terminal. After that, we will return to Apache to and CGI. So, when we open the terminal, clear the screen, and enter a command, such as ls, the program located in the bin directory is launched. In Unix-like operating systems, the actual location of the binary can be found using the command which ls. That is, if we enter which and the name of the binary we are looking for, we will see where the binary file is actually located in the file system. So, it doesn't matter to us what language the ls program is written in because, as I described earlier, all programs in the terminal are launched according to the same principle. That is, the bash shell makes a fork call and splits. In the child process, exec is called, which replaces the instructions and data of the child process with the specified program. In our case, this is ls. The child process receives environment variables, call parameters, and I/O streams from the parent process. In other words, all POSIX-compliant programs in Unix-like operating systems run according to the same principle. They receive command line arguments, data from stdin, and environment variables as input. Output data is transmitted via stdout, stdir, or third-party channels such as files, sockets, and the like. But let's see how it looks in practice. Let's create a script in bash. Let's paste the content here, save the file, and make it executable. To do this, we use the change mode command. Now let's go back to the body of the file and look at its content. Here we see a special bash command, $grid, which allows us to display the number of arguments. After that, there is $dog, which allows us to get a list of all arguments that were passed to this script. And the cat command, which reads data from stdin. Cat simply reads the entire input stream, whether it is a single line or multiple lines. And it doesn't matter what kernel object is used as the source, whether it is a file, pipe, or keyboard input. That is, when we call this script directly by its name, or when we add an interpreter specification here, to which we will pass this script name, although this is not necessary, because we have a shebang in the script that already specifies which interpreter should be used for this script. So, regardless of how we call it, we can pass input data in several ways. For example, we can write echo and pass what echo returns to pipe. Pipe is a vertical line. We specify some content here. We can pass it this way. Alternatively, we can pass the input stream from a file to the script. It will look like this. Or we can choose not to pass the input stream, just run this script, and then we will be prompted to enter data from the keyboard. We will cancel it from the keyboard and pass the data for all streams to this script. We will immediately specify echo and pass it to the pipe. Next, we will create an environment variable. That is, here we simply create a variable and set a value for it. In other words, we are simply creating a variable in the parent shell process. It has no relation to the script we are about to run. Next, we run the script itself and pass several parameters to it. 3, I think, is enough. Let's run the script. What do we see? If we scroll up, we see 3 arguments. That is, all the arguments we passed are recorded here. Here are parameters 1, 2, and 3. Next, we see the content we passed for the input stream. And if we look at the environment variables that were already available to this script, we see the variable myvar here. And, as you probably remember, all environment variables are passed from the parent process to the child process. That is, despite the fact that the myvar variable itself was created in the parent process, it became available in the child process. Great, let's move on. Well, it seems I forgot to show and explain one of the commands. Yes, after cat comes the env command, which, in fact, outputs all environment variables. Well, that's all there is to this file. We can move on. Similarly to the bash script, we can create a PHP script and run it in the terminal as well. We already have the PHP script itself. Let's just edit it. I will insert the content here. If you look at the code, we use a special array that is embedded in php-cgi, which records the number of arguments. We also have a special arg array, which lists all the arguments that are passed to the script. Next, using the file getContent function, we read from the PHP pseudo-stream stdin. And if you remember from the slides, PHP uses either constants or the stdin pseudo-stream, which can be read as a file. Next, we print the server variable, which contains all environment variables. Okay, let's save the file and exit. Let's make it executable, also using the change mode command. We will also launch our PHP script PHP, transferring data to all possible sources. We will also transfer some content via pipe. Next, we create a variable. Let it be myvar2 equal to myvalue2. And then we call the script itself. Let's pass him a couple of parameters and run our script. Scroll up. Here we can also see the number of arguments available in the script. Next, all arguments from the arg array are listed. The only distinguishing feature here is that the name of the called file itself is included in the arguments. We also see the content for stdin, which we read through the getContents file. Let's take a look at the variable environment. Here we can immediately see myvar2, which has the value 2. It is also available in the body of our script. This leads us to conclude that our PHP script was run exactly according to the same rules as the bash script in the terminal. At this point, I would like to make a small clarification about how input-output works in Unix-like systems. As mentioned earlier, each process inherits a table of file descriptors from the parent process. Usually, this is the bash shell, which in turn generates them at startup. This is 0 stdin, 1 stdout, 2 stdrr. Next, the process simply writes to descriptors 1 and 2 or reads from descriptor 0. It does not know where the data actually goes or where it comes from. By default, it is the terminal, output to the screen, and input from the keyboard. What exactly will be the source for file descriptor 0 and the receivers for file descriptors 1 and 2 is determined at the start of the process. The kernel has different types of input-output objects. These are files, terminals, pipes, sockets, and so on. Any of them can be used as a source or receiver of data. For example, we can edit our script in bash. Let's clear the screen and open the script. So, let's delete all the content and paste in the new one. Here we will only have a shebang, which specifies which interpreter should process this script, and also the cat command, to which we pass the input reading from the pseudo file dev.std in. Save and exit. Next, we can pass some content through the pipe and call our script to get the output. In this example, we sent the string content for std into the pipe. This pipe was set up when the bash process executing this script was launched as the source for descriptor 0. Then we read the pseudo file dev.std in, which is a reference to the projection of the descriptor proc self ft0. We can see this clearly. Let's read the dev directory. And here, if we scroll up a little, we will see 3 files. These are stdir, stdin, and stdout. All of them are references to the descriptor projection, where self dynamically points to the current process. In other words, through the descriptor projection, we ultimately obtain the contents of the pipe, which is the source for descriptor 0 in the current process. And if we run the same script, but do not set the pipe as the source, let's clear the screen and just call our script. But let's cancel keyboard input. To do this, enter Ctrl+C, and for testing purposes, we can try another option, namely redirecting stdir error output and simple stdout output to files. Let's create 2 files for this. I am only setting 777 permissions for testing purposes. In normal practice, of course, this is not necessary. Next, let's edit our bash script. Let's replace the content. Here I wrote a simple algorithm. We simply check that if a 1 is passed in the parameter, we will write the word success to stdout. If 0 is passed, we will print the word error to the stream with decryptor 2, that is, stderror. I made the default branch just for beauty. It will not check it. Let's go back to the terminal. And now let's call our script. I passed 1 as a parameter to verify successful launch. I also specify at the start of this process that I am directing the output stream to this file, and I am directing the stdir output stream with an error to this file. Let's launch it and view the contents of the log success file. We can see the word success recorded there. As we can see, nothing was printed in the terminal. Also, if we run our script and pass 0 as a parameter, nothing will be printed in the terminal either, but we will see the word error in the log error file. From all that has been said, the following conclusion can be drawn. When a process is created, a specific kernel object is assigned to each file descriptor. That is, it is a file, pipe, terminal, socket, and the like. By default, it is a terminal if the call occurs in a terminal. The process simply writes to the descriptor, for example, the first one, and behind it lies one or another kernel structure. The dev.stdin, dev.stdout, and dev.stdir files are symlinks to the file descriptors of the current process. It is also important to note that PHP scripts may encounter problems when attempting to read or write directly to dev.stdin and dev.stdout files. However, since there are convenient analogs, namely pseudo streams such as php-stdin and php-stdout, it is best to use them instead. Now let's return to our PHP script. As I mentioned in the theory section, SAPI generates a profile that corresponds to the execution environment. In all of our tests, we are now running the PHP interpreter with CLI SAPI. So we can take a look at the super global arrays available when using CLI SAPI, as well as the tools for working with input-output. Let's edit our script, clear the screen, replace the content, and look at the code I inserted. We also see the variables arg and arg here. One stores the number of arguments, the other stores the arguments themselves. Next, we see the superglobal array server env request. That is, all the superglobal arrays that you have to work with, all the ones that are created at startup. I also output the stdin, stdout, and stder constants here to see if they contain file descriptors or not. I also start reading from the sudo stream stdin and write to the sudo stream stdout. Let's save the file and call this script, passing all possible data. That is, we will use echo and pipe to pass a string that will go to stdin. We will also assign a variable here in the parent process and pass the parameters. Let's run the script and scroll up. And we see that we have 4 arguments. Next, we have a list of arguments that were passed. I would also like to draw your attention once again to the fact that, unlike Bash, when PHP is launched in CLI SAPI mode, the name of the script will also be passed as an argument. The superglobal array is defined and filled. As we mentioned in the theory section, the env array is empty, that is, it is defined but empty, because no arguments were passed to the script. Next are also defined but empty arrays. The globals array is also defined and set. It is always present in all profiles. The globals array is a general collection of all variables created within the running script. Session is an empty array. File descriptors are set. Next, we read from pipe content for stdin and also wrote a string to the output stream. In other words, from a PHP programmer's point of view, CliSPI created exactly the data and stream profile we expected. You may have questions about pseudo-streams and descriptors, and when to use them. Here is a short answer. If you need to work with files, use php-stdin and pseudo-streams. If you need to work with resources using a file descriptor, for example, using the fright function, then use constants. Now that we have covered launching programs in the terminal, the general principle of working with input-output in Unix-like systems, and the CLI profile, it is time to return to Apache2 and CGI. As I mentioned earlier, CGI developers decided to use the principle of launching terminal commands, but with a slight difference. CGI does not work with command line parameters. In the CGI protocol, the HTTP request is simply parsed, and the start line with headers is set in the environment variables, while the body of the request goes to stdin. In order to implement work with the CGI protocol, we need to install the CGI SAPI interpreter. Let's clear the screen and enter the installation command. We agree to install additional packages. Now, if we look at the directory with the PHP, we will see configurations for 2 installed interpreters, CLI and CGI. The next thing we need to do is change the configuration for the Apache2 web server. It is located in Apache2, sites available 000 default. Open the file. Here, we will add the following 3 lines. Specifically, we have set up alias. When accessing the CGI bin path, the var www.cgi bin directory will actually be requested. We will also create a handler PHP file for the PHP extension and set up the action. When accessing PHP files, the php-cgi runner file from the CGI bin directory will be executed, which, as we remember, will actually be the www.cgi bin directory. Save the file and exit. The next thing to do is to activate the modules for Apache2. We need to activate the Actions module and also the CGI module, and then restart Apache2. To do this, use the following 3 commands. Let's do it. Next, we need to go up one level and create a new CGI bin directory here. We'll use the make-dir command. Don't forget about sudo. The directory has been created. Next, go to this directory and create a file that will be our runner. Next, we just need to insert a shebang line that will specify which interpreter to run when attempting to launch this runner. Save the file and exit. Next, we will make this file executable. Then we will return to the HTML directory to change our script to PHP. Let's replace the content. Let's take a look at the new version of the script. Let's scroll up. Here, I added some checks so that arrays that were not defined at the start of the script would not cause an error. This applies to the argc and argv arrays. I also created similar conditions for constants because they will not be initialized in CGI mode, and accessing them will result in an error. But in order to clearly see that they are missing, I left them simply through if. Next, I attempt to read from the PHP input pseudo stream and write to the PHP output pseudo stream. Also, for clarity, for the test, I try to read from std in and write to the std out pseudo stream. Let's save the file and try to run our script using the CGI protocol. That is, we will send a request to the web server via an HTTP client, and the web server will call the php-cgi runner file as a separate process. The php-cgi runner file specifies the shebang bin env php-cgi, which means that the php-cgi interpreter will actually be launched. It evaluates the variable environment and understands, based on the file header content, which file we are trying to launch, and executes it independently. Well, let's execute the request and see the result. I am making a request specifically for the script.php file. That is, I am not addressing the php-cgi runner, but simply addressing the file that we have in the www.html directory. Let's make a request. And what do we see? We see that the argc and argv variables are not declared, as expected for a web profile. The server array is declared and populated. Next, the superglobal array end is declared but empty, as its filling is not included in the php-ini file. The next superglobal arrays are get requests. They are initialized and filled. The next array, post, is declared but empty. This is natural because we are making a request using the get method. If we make a request using the post method and pass some data in the request body, we will see this data in the superglobal array post. That is, in PHP, if the request is made using the post method and there is a request body, it can be obtained from the superglobal post array or directly from the input stream. If the request is made using other methods, such as put or patch, the request body is only available from the std and input stream. Let me remind you that when using CGI, the web server parses the HTTP request and places the headers and the start string in the variable environment, which will then be passed to the running process. The body of the request, if any, is sent to the socket, which will then become the source for the std in stream. The following superglobal arrays cookie, files, and session are currently empty, as we are not transferring any data for them. To briefly touch on this topic, data will be sent to the cookie array if the corresponding header is transferred in the HTTP request. That is, if we first set the setCookie header from the script using the setCookie function of the same name, and then the client, for example, the browser, sends it in subsequent requests to this server. In other words, it is a means of storing state between requests. The session array will be filled if session support is implemented. That is, using the special session start function, we create a file on the disk and write its identifier in the response header. The browser also sends us this identifier in subsequent HTTP requests. PHP searches for a file with the corresponding name and reads its data into the session array. In other words, working with sessions is not something independent in the HTTP protocol. There is no such concept in the HTTP protocol at all. It is simply a combination of cookies and a file on the disk. Sessions are also needed to preserve state between different requests, but with regard to private data. This is, of course, a simplified description of how sessions work, but it is essentially correct. Next, we have the superglobal array globals. It is both declared and filled. To reiterate, it is simply a collection of all declared variables in the running script. Let's scroll down. And we see that the constants stdin, stdout, and stdr are not declared, because their use is not provided for in the web profile, that is, according to the CGI protocol. And finally, we see the use of pseudo streams. This is PHP input, which allows you to read the body of the request. Now we see similar data in it with the post array. This is a PHP output pseudo stream, which allows to write to the output stream, while the stdin and stdout streams are zeroed. They will only be available in terminal mode, that is, when working with CLI SAPI. Well, that concludes our discussion of CGI, and we will now move on to FastCGI. At this point, we have an HTTP server that can distribute static files such as HTML and CSS. And if we need to run a program on the server, we can use the CGI protocol. In this case, our server will simply run the process for each request according to the general rules for running programs in the terminal. The launch process will execute its algorithm and return the result. It will contain the response headers defined in the script, as well as the body. The server will package all this into an HTTP response, combining it with its own headers, and return it to the client. However, this option proved to be suboptimal due to increasing loads. In other words, creating a process for each request became too time-consuming. The solution to this problem was the creation of the FastCGI protocol, in which there is one constantly running daemon process, and the server communicates with it over the network. This means that the scheme involving process splitting and data transfer to a child process will no longer work. The web server and php-fpm will exchange messages over the network. Essentially, the web server also parses the HTTP request it receives and extracts its start line, headers, and body. It then packs all of this into a special binary format and sends it over the network to the running php-fpm daemon. In other words, the server sends the same data as when using CGI, but in a different format. Inside php-fpm, SAPI parses the incoming message and lays out the data in accordance with the standard web profile. A link to the specification describing the FastCGI protocol is available in the text version of the video. I will add it to the pinned comment. We will simply examine a fragment of this specification. Here we see that the web server packs the same data, such as server port, server header, and so on. In the FCGI params field marked with the number 1, which we can see in the server array when working with the CGI protocol. That is, the same data from the environment variables. It also transmits the request body, if any, in the FCGI stdin field marked with the number 2. In response, php-fpm returns a result containing headers and body marked with the number 3. But let's take a look at how this works in practice. First, let's install php-fpm. To do this, return to the terminal and execute the command sudo apt install php-fpm. Agree to install additional packages. Once we have installed php-fpm, we can go to the etc php 8.4 directory and view the directory contents. We can see that an additional directory with fpm configurations has appeared here. If we go to this directory and print its contents, we will see a set of files and directories. The most important directory for us is conf.d. It contains the configuration ini files for the installed PHP modules and the pool.d directory. It contains the configuration of pools, that is, a set of running interpreters, workers, and daemons working in this process. In other words, php-fpm runs a pool of interpreters. It also has a master process that distributes incoming requests among workers. So, you can configure the running pool in the pool dwww compare file. Next, we need to install the Nginx web server. But first, I will remove the Apache2 web server. I will enter the password and agree to remove all packages and dependencies. After the Apache2 web server has been removed, you can install Nginx. Agree to install the dependencies. Now, the Nginx web server is installed. Let's try a test run. Enter localhost 8888. We see the welcome page of the Nginx web server. If, for example, we try to run a PHP script, we will see that the server was unable to process it. It returned its contents to us. That is, we see a similar situation. Nginx also looks in the www directory by default. And it does not know how to run PHP code, it just returned its contents. So let's do some basic server configuration so that it can send php-fpm requests when a client accesses PHP files. In the future, I plan to make a separate video dedicated to the Nginx php-fpm bundle, so for now, we will just give a brief overview. All Nginx configuration files are located in the Nginx etc directory. If we identify the main configuration points that require understanding, the first is host configuration. These are located in the site available and site enabled directories. In site available, we create a physical file with the host configuration. And if we want Nginx to apply it, we need to create a link to it in the site enabled directory. The second is the default enabled config. It is located in the etc Nginx directory, site available default. Let's open this configuration file. Let's enter the password. For basic configuration, we only need to enter a few lines. Let's scroll down. Here we see that there are already commented configurations for running PHP, but we will insert our own configuration. If you look at the settings we just added, there is a FastCGI pass that specifies the socket address through which Nginx will send requests to the FPM process manager. That is, if php-fpm Nginx runs on one machine, messaging can go through a socket. But in production, all this often works over the network. The second directive is include, which enables the standard configuration for processing PHP scripts via FastCGI. Let's save these changes and exit. After entering our configuration, we need to restart the web server. Now we can reopen Postman and make another request addressed to our PHP script file. As a result, we get a working combination of Nginx plus php-fpm. And if we look at the data, despite the fact that we ran the PHP code in a different environment, we have a standard web profile similar to that provided by CGI SAPI. That concludes our discussion of FastCGI, and we will now move on to the conclusions. As a result of this analysis, we understood the difference between compilation and interpretation, and divided the concept of PHP into language and interpreter. We analyzed the three main components of the interpreter: SAPI, Zend Engine, and extension. We have understood the fundamental principle of launching programs in the terminal and its derivative CGI. We have briefly familiarized ourselves with FastCGI. Based on all of the above, I have constructed a map of semantic entities that make up PHP technology. The first is execution environments and interaction architectures. This area may include topics such as console utilities in PHP, web implementation on Nginx php-fpm, and also web built on alternative approaches such as Roadrunner, AIM-PHP, or Swool. The second is working with the core. This may include implementation stages, methods for acceleration and optimization, and working with core functionality extensions. The third is working with code. This will cover the basic techniques and patterns for applied tasks, testing and quality control tools, Composer, and the package ecosystem. The fourth is frameworks. Here, you need to understand the big picture, that is what it is and why it is needed, and be able to apply it in practice, for example, Laravel as a special case. The fifth is PHP in the context of the operating system. The main topics here will be processes, sockets, system calls, the file system, and the input-output system. In this series of videos, I will delve into different areas and conduct research there. There will be no strict order of progression, everything will be based on inspiration. You can either follow along with me or dig into different areas on your own and put together your own puzzle of understanding PHP based on this map. In general, this was a picture of the inner workings of the world of PHP. But as the cherry on top, let's step away from PHP for a moment to see an even more global map. PHP is just one part of an ecosystem that exists within the larger space of an operating system. It is just one fish in this aquarium. The scope of the operating system is much broader than PHP. Fundamentally, the work is done within the operating system. It runs on a physical server. Within the OS, usually a Linux family, one of the technologies is a web server that receives messages from the outside world via the network. The web server receives messages from the outside world via the network. Behind this web server runs PHP, most often used as a link between the web server and the database management system, although other server languages often serve as such a link. In other words, the main battlefield is the operating system, and within it, sets of technologies are configured that operate according to its rules and solve applied problems. In this series, we will mainly talk about PHP, but we may have to go beyond its scope in some places for the sake of clarity. That's all for now. If you found this material interesting or useful, don't forget to subscribe to YouTube channel and give us a thumbs up. If you're using the text version of the video, don't forget to give us a star on GitHub. Thank you, everyone. Bye.